All right, well, thanks first to the organizers for the invitation to come and speak, and glad to be finally here. So, slight disclaimer here, I've been traveling for 32 of the last 48 hours, so this might be a little rougher than I had hoped, but please ask questions if things are unclear. So I'll be talking about trying to make more precise a phenomenon that was observed a number of years ago related to the Steinmann relations, which I'll describe in more detail in my talk. But the basic idea is that there are certain types of analytic relations that Feynman integrals and scattering amplitudes in general obey that are violated in specific situations involving what I'll call two-particle momentum channels. And so this was observed maybe 5+ years ago, and not much has been done with it since, to my knowledge. So the idea of today's talk is to make more precise when exactly this happens so that we can make predictions then as we're trying to compute further integrals. So this is work in progress, I should say, with Hofi, Luke, and Maria, who's here. So please ask both Maria and myself questions about this after the talk. It is work in progress, so this is not the final story, hopefully. So some of the statements I'll make will be, I'll be a little conservative in what I say, but I'm hoping these statements can be made stronger in the near future. Okay, so briefly let me just motivate why we might be interested in studying the analytic structure of scattering amplitudes and Feynman integrals. So what that is to say, where these integrals become singular and can develop things like branch cuts. One motivation is conceptual. So it's long been believed that the analytic structure of these integrals is controlled by basic physical principles like locality and causality. But even though we can kind of see this in the simplest examples, fleshing this out in terms of concrete predictions for what the analytic structure of more complicated integrals looks like turns out to be incredibly difficult. So we'd like to develop our understanding conceptually of what implications these basic physical principles have. And then, of course, computationally, if we can make more refined statements about what types of analytic structure Feynman integrals should have, of course, this should pay dividends in terms of different ways of computing these integrals and amplitudes. In particular, I'm interested in bootstrapping these types of integrals, so trying to just write down a general ansatz that has these types of properties built in, and I'm trying to guess and constrain the answer directly that way. So this is kind of the intellectual background within which I'm studying these types of properties. However, the study of these properties of Feynman integrals and scattering amplitudes goes back over 60 years and is often referred to as Landau analysis. So let me begin by just kind of giving a brief intro into the types of properties we can study using these methods, which were pioneered by Landau. So one of the most basic questions we can ask in this game is just where Feynman integrals and scattering amplitudes become singular in the space of external kinematics. So instead of answering this directly for Feynman integrals, let me just address this for more of a toy model, just to make our life a little simpler, and then hopefully the way in which it applies to Feynman integrals will become also clear. So let me consider just a function of some variable s, which will be our stand-in for our external kinematic parameter. And we're going to integrate this, or it's going to correspond to some integral over a rational function g of x and s that appears in the denominator, and we're going to integrate it over some contour gamma. So let me see if I can get some colors working. Please tell me if these colors are not working for people in the back. Oh, that looks fine. So we have some contour gamma. Of course, this is just a cartoon here that exaggerates what it might look like in the x-plane. So my integration plane. And so one of the types of questions we can ask is when this function, f, can become singular as we vary this external parameter s, okay? So the first observation we can make is, so by assumption, this function g is going to be some polynomial in the variables x and s. And note, of course, this is how Feynman integrals start their life. We'll just have some propagators in the denominator, which will be polynomials, and the integration variables in the external kinematics. And so the first thing to note is that we don't expect this integral to be singular unless g itself is 0, because it's in the denominator, it'll give rise to a singularity. So the first thing we might do is just say, okay, let's think about g of s as being split up into a product of roots for any number of roots here. And then in this integration plane x, let's see if green works, we'll have some set of singular points, r1, r2, r3, etc., where if we sit on top of one of those points, the integrand becomes singular, okay? So the question we want to answer is, when does the function f inherit the singularities of the integrand? So as we vary this parameter s, so these roots here, r1, r2, etc., will be functions of our external kinematic parameter s. And so as we vary that parameter, what's going to happen is these roots are going to move around. And in principle, they can start to approach and even pass through the integration contour. So three possible things can happen. One thing that can happen is that one of these roots just passes all the way through the original contour, but in such a way that we can just deform the contour. So just using basic ideas from complex analysis, the idea is we can just pull the contour over here, and as long as we don't pass any other kind of analytic feature, this is a valid analytic continuation of our integral here. And so nothing actually happens. We can avoid this singularity in the integrand just by pulling the contour out of the way. However, we might encounter a situation where, let me redraw this path, where two of these singular surfaces approach the contour from opposite sides in such a way that we can't deform the contour out of the way. In this case, we will encounter what's called a pinch singularity because the integral itself cannot avoid the singularity that occurs in the integrand. And so then this function f of s at that point will indeed actually become singular. It can develop something like a branch cut, or it can have a simple pole, for instance. And the other final thing that can happen is we might encounter a situation where one of these singular surfaces approaches and intersects one of these integration endpoints. So this is what you might call gamma of 0 and gamma of 1 for the beginning and end point of the contour. And if one of these singular surfaces intersects the endpoint, we can't deform the endpoint out of the way. We can't change this contour in the endpoint without just redefining our integral. It would just be a different integral if we did that. And therefore, such configurations will also give rise to singularities at the level of the full integral. Okay, any questions on that? Okay, so let me formulate these ideas in a set of equations, which are necessary conditions for such singularities to occur, but not sufficient conditions in general. And I'm going to call them the Landau equations in quotes just because I'll formulate them for some generic function, functions f and g, but if you were to apply the same exact reasoning to normal Feynman integrals, you get what we normally call the Landau equations. So the first equation that we require, so we should be clear, we're talking about where in the space of both the integration variable x and the space of external variables s, a singularity can arise. So we're going to have equations here that constrain both sets of variables. And the first equation is just going to be that we need to be at a point where this function g of x and s is 0, because of course that's where singularities occur in the integrand. Yeah? So you can have, right, so one thing you can always do, of course, is break things up into one-fold integrals, and then I think this picture holds. It's a bit harder to do the, to illustrate the more general picture, but I think conceptually this is all that can happen. You can have self-intersection of surfaces, but you can think of that as some product of roots, if you will, morally speaking. Okay. Okay. So this is our first equation. The second condition is what we want to use to say that either a pinch of the contour is happening or we are at one of the endpoints. So I can do the following. We'll have a pinch of the contour if the following condition is satisfied. Now the idea here is the following. If the function g is just a product of roots, and I'm at a position where two of the roots are sitting on top of each other because they've pinched the contour, then when I take the derivative of this function g of s by the product rule, I just get a sum of a bunch of different terms, each of which involve all but one of these roots. And if two of them are vanishing, that means every term in the sum will vanish. So if this is satisfied, then we're at a point where a pinch can occur. And then we can also have endpoints. So it can also be that x is sitting on top of gamma of 0 or gamma of 1. So these equations will solve for both x and s. Yeah, so in the example where we truly just had a single variable s and a single variable x, we've got two conditions here, and that would fully tell us what value s has to have for instance, two of these roots to pinch the contour and where that pinch is occurring in the space of x variables. Good. Any other questions? Oh, just because I only require one of the two things to happen. Either we're at a pinch is occurring, or we're at an endpoint. So I'm just including both potentials and potential situations in one equation. In practice, I would, study them one at a time. Yeah. Yes, this is a necessary set of conditions, not sufficient. Indeed, because it could be the case that we have roots way out here that sit on top of each other, but the contour is far away. So in that case, we wouldn't get a singularity, and that will come up in a few minutes. I'll be highlighting that again. Any other questions?
Can you tell us something more about this integral? So there is an option of having the denominator being 0.
Yes.
For all s's at the endpoint.
That's true.
So do you assume that it exists for some s?
Oh yeah, so I should have, if I was being a little more careful, I would have said something like that this integral is well-defined and finite for some s, and then I can analytically continue from there. There will exist solutions to these types of equations for Feynman integrals that are true for all the external kinematics. Those will be IR singularities, but I won't be saying much about those in this talk. Yeah, I'll be focusing on solutions to Landau equations, or stated differently, singularities that only occur for a specific value of the external kinematic variable or variables. Any further questions? That's true. Good. That's another situation that can occur. Indeed, you might have this root approaching from the same side, and then again, you wouldn't have a pinch, which again is stating the fact that this is a necessary set of conditions and not sufficient. That's right. Thanks. Any more questions before I go on to an example? No, it's not easy to formulate a sufficient set of conditions. You can, in any given example, in principle, work it out, but nothing succinct like a set of equations like this. Yeah. I mean, one algorithm for finding a sufficient set of conditions is to compute the answer and see what singularities arise. That's probably the most efficient method we have at the moment and most reliable. All right, any questions? Good. Okay, so let me consider the following example, the simplest Feynman integral we might consider, just the bubble integral. So we have some momentum p coming in. I'm going to give the two propagators different masses so that everything is finite in 2 dimensions. I'll study this integral in 2 dimensions. And just so that I can illustrate something, an example that looks a little more like the toy model I just talked about, let me go to Feynman parameters. So we can do that by introducing a pair of Feynman parameters for these propagators, and then this will give us a projective integral, and I can get rid of one of the Feynman parameters by setting the sum of them to 1. So I'll do that all in one step. This is hopefully something that we've all seen in a quantum field theory course. My new integral will look like this. Okay. Where S here is p squared, the square of the external momentum coming in. Okay, so we can apply the Landau equations in this example, first by requiring that the denominator vanishes. So because it will actually be useful to plot this, let me tell you exactly what that requires. Oops. Although the details here aren't so important, the important point is to get across that we just have an explicit equation for what the value of these roots is as a function of s and the m's, because that is going to be what allows us to translate back and forth between what's happening in the space of external kinematics and the space of integration variables. So this is the set of alphas that just set this denominator to 0. And then, of course, we also need to be either at an endpoint or at a potential pinch. So let me go to the pinch solution, which is going to correspond to the case where both of these two propagators are on shell. And if we further impose that condition, we'll find the constraint that S is equal to M1 plus or minus M2 squared. Actually, let me just do the solution separately. Then we'll have that the two roots meet at M2 over M1 plus M2. Or in the case of the so-called pseudo threshold, where we get the difference of the two masses squared equals to S, then the roots will collide at M2 over M2 minus M1. Where I think I've assumed here that M1 is greater than M2. Okay, so all I've done is solve these two equations, in particular requiring this branch of the second solution. And now I can ask what happens as I analytically continue my integral around this potentially singular point. So I'll use colors again. In the S-plane, okay, we'll assume that the masses of the particles are fixed. In the S-plane, we have a branch cut structure that looks like the following. We have some branch cut that starts at the threshold where S is equal to M1 plus M2 squared. And so we can ask what happens as we analytically continue. Let's say we start with our Feynman integral at some point here. Our S is above the branch cut. And we analytically continue to the situation where this point is just below the branch cut. So in the integration variable plane, the alpha plane, we can just use this equation to track exactly what's going to happen with the two roots, which correspond to the singular surfaces, and I want to, keep track of whether they're going to pinch the integration contour. So we recall that the integration contour is just between 0 and 1 in the alpha plane on the real line. And the two roots are going to end up doing the following. We have alpha plus just above the real axis, and we have alpha minus just below the real axis. This is given by the I epsilon prescription, which I haven't been explicit about, but we can track this. And what's going to happen is these two roots are going to rotate around the point where they would collide if we sent S exactly to this value. So this is going to be given here by M2 over the sum of the M's. I'm looking at this solution. Sorry, I wrote down two solutions. There's the threshold solution and the pseudo-threshold solution. I won't use the pseudo-threshold yet. Thanks for the clarification. So this is the threshold solution, which does exist on the physical sheet because it is kinematically an accessible process that can happen here. If the momentum squared coming into this diagram is large enough to create a pair of particles of mass M1 and M2. So we can track exactly what happens into the integration plane. And so in such a way, we can ask what is the discontinuity of this Feynman integral across this branch cut, right? We can track what the value of the function is above and below. And that's going to correspond to integrating the Feynman integral along the new integration contour minus the original integration contour, okay? I'm just taking the difference of the function after minus before the analytic continuation. And what's happened here is the two roots have traded places. They've only rotated around half a circle due to the fact that we have the square root. So even though I've sent S around a full circle, the two roots have only gone half a circle. And the new integration contour is going to be bulged out in a way that I'm exaggerating here to avoid these singular poles, okay? So that means that the discontinuity with respect to the threshold of this integral is going to be given by the new contour minus the original contour of the same integrand. But tracking the difference between these two contours, so we have that gamma prime minus gamma is just equal to this bulged out contour minus the original contour, right? And so what's going to happen is the difference is going to be given by these two small circles, which are effectively going to take residues around these two roots of the denominator. All right. Was that move reasonably clear? Okay. Okay, so the point of working through this example was now I get to illustrate two types of analytic constraints that we might now derive for in this simple example, which will generalize to much more interesting classes of constraints and higher loop diagrams. The first type of constraints is what we call hierarchical constraints. So these constraints are, they follow from realizing that after we've taken this discontinuity, there will be some singularities of the original Feynman integral that can no longer be accessed, no matter how much we analytically continue. If we allow ourselves to do anything with the analytically continue our variables in an arbitrarily complicated way, we will just never see these singularities. So in this example, this corresponds to the fact that after we've computed a discontinuity with respect to the threshold singularity, well, there were singularities associated with setting one of these masses to 0. These corresponded to endpoint singularities. I didn't highlight this, but if I were to set one of these masses to 0, we would see that, let's say I set m1 to 0, for instance. Then if I set alpha equal to 1, both of these remaining terms would vanish, and that's an endpoint singularity. But look, our new contour, our new integration contour that gives us this discontinuity no longer has an endpoint at 1. So that means that no matter what I do to my new integral, I cannot possibly get a singularity when m1 is equal to 0 like I could in the original Feynman integral. So this is what we call a hierarchical constraint. It has a slightly different avatar in momentum space, which is worth highlighting because this is how in the literature it's been more traditionally talked about. So let me quickly write that down. Not in 2 dimensions. That's a second type singularity. I think it doesn't appear in 2 dimensions. I'm not going to say anything about that, though.
Okay, so basically already the way you were presenting this equations, I think great, but you can get exactly the contour integration pushed to infinity.
Sure.
So your second type singularities do not play at all.
I'm not going to single them out, no. I'm going to end up focusing on Steinmann relations, which only care about the first 2 entries. And so loosely speaking, while second type singularities can appear, I'm not going to be quite as worried about them as if I were thinking about the 6th or 7th discontinuity. But yeah, I'm not going to have anything specific to say about that. But they can exist, I agree. Good, so again, just to highlight the avatar of these hierarchical constraints in momentum space, if we were to play the same exact game, but apply it to the loop momentum form of the integral, what we would derive is what hopefully many of us have encountered as Kutkowski's formula, where these propagators would be replaced by delta functions. So in this example, we would have gotten discontinuity with respect to the threshold is equal to just the same integral, but now we've got in place of the propagators these delta plus functions where the plus refers to the fact that there's some positive energy constraint or constraint on which direction the energy is flowing in. So in these cases, the way in which the lack of endpoints shows up is that now we're constrained to the on-shell surfaces associated with these propagators. So in this correspondence can be made more general. In Feynman parameter space, the hierarchical principle is a statement about endpoint singularities no longer existing. In momentum space, it becomes a statement about singularities no longer being kinematically accessible, no matter how much we want to analytically continue, based on the fact that we need to stay on the support of these delta functions. And so that's how people often talk about it, is these singularities are not kinematically accessible. Good. The whole this continuity, you mean? Yeah, in this case, I'm assuming that I started in the physical region where S was greater than M1 plus M2. But then once I've computed this discontinuity, so let's say I specified a given region, the whole point here is that no matter how much I allow myself to analytically continue onto new sheets, I can never access the singularities in the masses. Sure, sure, yeah. I'm just trying to motivate the class of constraints. Any questions on that? Any further questions on that before I get to the second class of constraints? Okay, so the second type of constraints has the opposite way, or we have a different way of thinking about it, which is it may be the case that in the current, on the current sheet, given the current integration contour, a given singularity may or may not appear, but if we allow ourselves to analytically continue in an arbitrarily complicated fashion, we can find that singularity again. So these are often referred to, or can be referred to, as adjacency constraints, because they're telling you something about what sequences of discontinuities can appear in the Feynman integral, what discontinuities can follow one after the other. And so in this example, in the bubble example, we have such a situation happening with the pseudo threshold. So the pseudo threshold cannot appear on the original physical sheet. One way of seeing that is that in the space of Feynman parameters, the roots are going to be negative, and so it's going to be a pinch that happens somewhere here, and it won't pinch the contour. But once I've computed a discontinuity with respect to the threshold, my new integration contour is just a small circle around both these residues, or sorry, around both of these poles, which looks like a pair of residues. And if I imagine now analytically continuing my kinematic variables, or S back to this pseudo threshold point, you can see that what's going to happen is these two roots are essentially, let me just draw it actually. These two roots will now move back here and pinch back there. But since the contour of the discontinuity is these two small circles, we will get a pinch. So this pseudo threshold is a discontinuity of the threshold discontinuity. So this is an example of an adjacency type constraint where it couldn't follow the kind of the null discontinuity, if you want, of the original Feynman integral, where we hadn't taken a discontinuity, but it can follow once we've computed a threshold. So these are the two basic classes of constraints we talk about when it comes to Feynman integrals. And let me just highlight the kind of current state of play with both of them. Are there any more questions in the meantime? So both of these types of constraints were, at least examples of them were understood over 60 years ago, although those results mainly are restricted to cases that involve generic masses. The proofs there often assume things like non-zero mass gaps in the theory. So more recently, there's been quite a bit of progress in understanding how these constraints, these types of constraints can be generalized or understood in more general cases. So let me just highlight some of those. Uh-huh. Yeah. No, let's talk about it now because I'm just going to do some bullet points. So the point was that the pinch corresponding to the pseudo-threshold did not pinch the original contour. Once the contour has been changed, because I computed discontinuity with respect to the threshold, with the new integration contour, the same exact configuration will pinch the contour. Will pinch the contour. So in that sense, and if we were to compute in a more complicated example, maybe 3 discontinuities, 4 discontinuities, we'll get yet more intricate integration contours. And so the question of whether at any given point a given singularity is accessible, it's a hard question to answer. But I kind of group all such questions under this notion of adjacency constraints because it's addressing the question of after a given set or most recent discontinuity has been computed, can I access a singularity given the integration contour that I got from the last discontinuity? That's all I'm trying to get across here. And in general, that's, as you well know, a very hard question to answer in a given example. But at least we can talk about the class of constraints there. Any other questions? Good. Okay, so I just wanted to highlight kind of the state of play for these types of constraints to illustrate that there's been some interesting work in these directions. And then I'll focus more specifically on the 2-particle Steinmann violation that I highlighted in the title of the talk. So recently, the hierarchical constraints, which were formulated 60 years ago in terms of momentum space, have been formulated in Feynman parameter space. So that was done by Marco Berghoff and Eric Panzer. And so that's where I get the statement from. One way in which hierarchical constraints can arise is due to the disappearing of endpoint singularities. And then also, more recently this year, Maria and I, with our collaborators that I wrote on the first board, were able to develop some genealogical methods, which is some kind of algorithmic way of deriving many of the hierarchical constraints that follow from the hierarchical principle in Feynman parameter space. And it's worth highlighting this because in general, this was an unsolved problem in the sense that if you went and handed a given Feynman integral to a mathematician and asked them to work out these hierarchical constraints, in principle it could be done. In practice, it was difficult enough it had been done in maybe 5 examples, whereas here we could just put some questions on a computer and we don't get the full set of hierarchical constraints, but we get the vast majority, let's call it 90-ish% of them, for 10% of the work. And again, that was with Maria and my co-authors on the original slide. On the adjacency side, going a little further back in time, so maybe 5-ish years back in time, we have some more empirical work, for instance, the discovery of cluster adjacency in n equals 4 super Yang-Mills theory due to Drummond, Foster, Gerdogan, and similarly, but stated in a slightly different language, the so-called extended Steinmann relations. So since Yorgos is here, let me go ahead and write out the authors here. It's one of those interesting situations where you go back and remember people who were on the paper who you hadn't remembered were on the paper. because they left the field, not because they didn't contribute. Okay, so the idea here is that a number of observations were made, again, like 5-ish years ago, about adjacency type constraints, especially in the types of integrals that appear in planar n equals 4. The first bullet point here, cluster adjacency, is a way of formulating these constraints by interpreting the discontinuity loci of these integrals in terms of what are called cluster algebras. That would take me too far afield today, so let me focus a little more on the extended Steinmann relations, which in that context turn out to be equivalent up to some kind of empirical asterisks. And these extended Steinmann relations generalize the normal or kind of first version of the Steinmann relations, which were first proved back in the 60s for theories with massive particles. So first off, these extended Steinmann relations apply to massless Feynman integrals and scattering amplitudes. And they extend the original Steinmann relations, which were statements about double discontinuities, the first 2 discontinuities of Feynman integrals, to longer sequences of discontinuities. So if we were to first take 3 discontinuities with respect to some other variables, and then took a pair of discontinuities with respect to specific kinematic loci, we would get constraints from the extended Steinmann relations. However, I want to highlight that all of the work over here at the moment is still empirical, meaning we have plenty of examples. We're not worried that it doesn't hold, but we still don't have a proof for it. And so in particular, in the case of the Steinmann relations being applied in massless theories, there are known counterexamples. And let me highlight that for the rest of the talk, I will not be talking about the extended Steinmann relations, but just the Steinmann relations. So I'll be talking about the discontinuities, or what can be said about the discontinuities of Feynman integrals. Starting from the physical sheet, I'm not going to take longer sequences of discontinuities. And empirically, it's been known since these works that the Steinmann relations are violated in 2 particle channels. So let me first highlight that the statement of the Steinmann relations is a statement about what I'll call partially overlapping momentum channels. So if I have some kind of Feynman integral, I, and I compute a discontinuity with respect to some momentum channel, let's call it S1, 2, 3, where in general Sijk is going to be equal to the squared sum of these 3 momenta. We'll assume they're external momenta. So this would be some higher, let's call it 6 or 7 points, just so I have enough kinematic variables. So if it was 4 points, this would be equal to, by momentum conservation, to a 1 particle invariant, if you will. So I just want it to be sufficiently high by momentum conservation, right? If it was 4 points, I would just be able to relate the sum of these 3 to the 4th variable. So I just want to have sufficiently many external momenta that I can't do that. Other than that, I don't really care how many particles I have. This is going to be a general statement for any such case. So if I compute a discontinuity first with respect to, say, S1, 2, 3, and then with respect to S, let's say, 2, 3, 4, so I call these partially overlapping momentum channels in the sense that they contain some of the same external momenta, but they're not. It's not the case that one fully contains the other. Well, then this double discontinuity by the Steinmann relations is supposed to vanish. However, in certain cases involving what I'll call 2 particle invariants, and when I use that language, I'm focusing on the massless case. So these will be 2 massless external momenta, but of course, if I put them together at a vertex, they would kind of resemble a mass. So I'm just saying that to clarify my language here. It's been observed that in some cases, let's say If I took a discontinuity with respect to S12 and with respect to S234, so again, they're partially overlapping. In general, such double discontinuities that involve two particle channels do not vanish. And at the moment, this remains an empirical observation, and not much has been done to make this more precise. We just kind of have observed this fact, and so we don't worry about Steinmann relations that involve two particle momentum channels. So the rest of my talk is going to be about trying to make this statement more precise, when this happens more precise, and give you a graphical way of deciding in your favorite two-loop Feynman integral if this will happen or not. Okay? Any questions on? Okay. Well, clearly it's not covered, but neither are any of these massless cases either, and we're happy to use them. So I would say it the following way. Let's see if you agree with this characterization, that thus far we've all been happy to go around saying that this is due to some kind of constraint on the space of allowed kinematics, where we, some restriction on how things can be analytically continued, but I don't think we've ever made that more precise. And I don't know how to make that more precise at this time. So my goal here is not actually to explain this theoretically, but to give a practical understanding of when it'll happen, which has not been done, to my knowledge. No, yeah, sorry. Anything involving only 3 and higher particle Mandel-Steinmann invariants, this is satisfied. It's only cases involving one or both 2 particle invariants where this can possibly happen empirically. Maybe, but I can't make that more precise at this time. But it might be. No, I don't have anything prepared. I think there may be something like that, but that's actually not the direction I'm going to be heading today. Yeah. All right, well, I'll give you an example. I'll give you some examples. Oh, that's fine. Yeah, I'm not claiming that this type of thing doesn't happen for the massive case. I'm just ignoring the massive case for now. I'm just trying to make the massless case more precise. Yeah, that's not a statement that I don't think this happens there as well. In fact, I can write down examples where it does happen, but I just won't have a complete story there yet.
My understanding is the issue with these statements is that you cannot take a discontinuity to one variable and then the other, because those two are not independent.
Yeah, I've also used those. Yeah. I won't, but I'm also comfortable using those words in talks, but in practice, I don't want to go and work that out in given examples when that's the case, right? So that's why I'm going to try and present a different way of thinking about the problem, which is easy to replicate, rather than going and trying to analytically continue in these high-dimensional kinematic spaces. I don't disagree with what you're saying. I just don't think it's a very useful way to make any predictions in practice. Yeah. Any other questions? All right. All right, very good. So the classic example of a Steinmann violating Feynman integral for those of you who maybe have thought about this, is the massless box. So no internal or external masses. So let me begin by just trying to illustrate how Steinmann violation arises from a Landau analysis point of view in that example. So we have this example here. And empirically, it's the case that the discontinuity of this integral with respect to s equals 0 and then t equals 0 vanishes, where I'm calling this s and I'm calling this t. So the first question is, how does this happen from the point of view of Landau analysis? So to see how this happens, we can think about just solving the Landau equations for the s equals 0 threshold. And what we generally expect from just any of you who have solved the Landau equations, what's going to happen is we expect to end up with, or in a situation where we have two propagators put on shell that we can think of as pinching the integration contour in momentum space. And we can parameterize the momentum going through these two propagators. So this would be, for instance, the top and bottom propagator. We can parameterize it as L, and then we have L plus P1 plus P2 going through the other propagator. And I'm not going to solve the Landau equations in front of you, but what you'll find is, first off, we're going to have the on-shell condition satisfied for both of these propagators. And this is going to give rise to a singularity at S, which again is equal to P1 plus P2 squared equals to 0. And moreover, when we fully solve everything, we'll find that the momentum flowing through this propagator is given by minus alpha 2 over alpha 2 plus alpha 4 P1 plus P2 as a vector, where my conventions are that these are how I've assigned Feynman parameters. Okay? So this is some solution of the Landau equations, which tells me where the singularity appears both in the space of external kinematics and in the space of integration variables. But we can immediately make an observation about this solution by thinking about the larger diagram that it's embedded in, namely this box integral. So if we were to think about the momentum flowing through the edges on the left and right of the box, so for instance, on the left, we're going to have L plus P1 squared. Well, if I expand that out, I'm going to get L squared plus 2L dot P1 plus P1 squared. And this guy is going to be 0 by the on-shell condition. This guy is going to be 0 because that's a massless external momentum. So we're going to end up with just 2 times, and then I can plug in this L. So let me call it minus 2 alpha 2 over alpha 2 plus alpha 4 times P1 dot P2 dot P1. Okay? Oops. P1 plus P2 dot P1. So this P1 squared is clearly going to vanish again because that's a massless particle. And the P2 dot P1 is going to vanish because of this condition on S, right? Because if I expand that out, we'll get P1 squared plus P2 squared, both of which vanish. And then the 2 P1 dot P2. And so this is going to be 0. So we see that even though we don't want to think of the propagators on the left and right of the diagram, which are labeled by alpha 1 and alpha 3, as participating in the pinch in the sense that the singular surfaces are actively pinching the contour, they're what we might call accidentally on shell. So on the support of this solution of the Landau equations, where the singularity happens, both the left and by symmetry, the right propagator are on shell. They can be off somewhere else in the space of integration variables, those singular surfaces. They're not actively giving rise to a singularity, but they're in a configuration such that the on-shell condition is satisfied. So what does that tell us? Well, if we think back to the Kutkovsky formula, if I were to have computed first a discontinuity with respect to t equals 0, what would have happened is I would have ended up with a formula in which the two propagators associated with alpha 1 and alpha 3 ended up in these delta plus functions, so they would be on shell when I computed a discontinuity with respect to t equals 0. Well, this fact that I'm telling you now, that when I solve the Landau equations for the s equals 0 singularity, that this solution is consistent with both of the other propagators being on shell, tells me that this s equals 0 singularity will still be accessible even after I've computed a discontinuity with respect to t. All right, that was a lot of words. Any questions on what I just said? It was a bit quick. Yes? I don't think so, because if I were to draw this diagram here, this would not occur, and the threshold and pseudo-threshold are sitting on top of each other there as well. Other questions? Okay. Oh yeah, totally. So no, this is a first type singularity. I told you what the loop momentum is, right? That's at a finite position. Although your comment is correct in the sense that if you started from a box with more masses around and took a limit, you would see in some sense the box singularity, which is conceptually distinct from the bubble singularity, colliding and sitting on top of each other. That is what's happening from the higher dimensional kinematic point of view. But if you just start with a massless box, you don't know any about that, you just find this and you observe this fact. Okay, and we have good control over one loop integrals, so we can go and ask this type of question more generally, namely, if I look at a pair of partially overlapping channels, namely the types of pairs of channels that we think might be that might satisfy the Steinmann relations. Yeah. But that's a projective. That's projective. So I can set alpha 2 to 1, for instance. I mean, in the tulip examples I'll talk about, there will be second type singularities of this type. I don't know. That doesn't tell me anything further, personally. They exist. Okay. So we can go and at one loop we can ask this type of question more generally. Namely, if I look at a pair of partially overlapping momentum channels, when does this phenomenon occur? Namely, if I were to think of taking one discontinuity followed by the other one, when is it the case that in both orders, the second discontinuity I should still think of being kinematically accessible in the way that this one was? And the answer is going to be that all such solutions to the Landau equations end up associated with diagrams that look like this. In fact, let me not even label the external momenta. And I'm going to put dots there, meaning that at those corners, I allow there to be any number of particles, at least one massless particle, though. So there could be a massless particle there. In both cases, that would reduce to the massless box again. I could also allow 2 or 3 massless particles there, and I still find such solutions. It'll be a different solution in those cases. I can write them down for you if you want, but they're probably not that revealing, so I will skip that for now. Come ask me later if you're interested. So I'm treating these as scalar diagrams. I've said nothing about numerators, so the punchline of my talk is going to be an if type statement, not an if and only if, because of the numerators. So I'll make that a little more clear. So yeah, let me make the statement here. In 3 minutes, I think you'll be satisfied. Thanks. So at one loop, all such solutions to the Landau equations that have this property come associated with this Landau diagram. So I think of having a diagram with a pair of cuts that looks like this. Notice that this left-hand side of the diagram was kind of dictated by the fact that I wanted at least one of my Mandel-Steinmann variants to be a two-particle Mandel-Steinmann variant, and that I wanted to have a partially overlapping channel. This means I needed to be able to cut it in half. But then these can have any number of particles associated with them. But with this observation, I can say the following. We expect that these, as a result, are the only cuts that can give rise to violations of the Steinmann relations. And so we now have a graphical way of predicting when this will happen. Namely, I go to, for now, just my one loop Feynman integral, and I look at what I'll call the set of minimal cuts of this diagram, and corresponding to the pair of partially overlapping channels that I'm looking at, and I'll ask if such a cut that looks like this exists. If it does, then Steinmann can be violated, will be the prediction. If no such cut that looks like this does appear, so for instance, at one loop the phenomenology isn't so interesting, but this would be an example. There'll be more interesting cases at two loops. But if no such cut does exist, then Steinmann cannot be violated. So this is where the fact that I have not considered numerators comes in. Is I'm not going to make it an if and only an if statement that if such a cut does exist, then Steinmann will be violated. That's not going to be the case in general because the numerators can come in and cancel off potential Steinmann violation. Oh, sorry, sorry. That was supposed to be non-zero from the get-go. Sorry, that the violation is that is non-zero. Thank you. That was a very important clarification. That's what I mean by Steinmann violation. The double discontinuity is not zero.
My question was more actually coming from like when you have I don't see the difference in having multiple particles entering at one vertex or just entering one vertex because it's just the momentum flowing in that's relevant, right? In the scalar case.
Yeah.
So it's just the sum of all the momentum.
That's right. Yeah. So yeah. That's right. It's just that, let's say I started with a diagram that looked like this. Okay, some high, one loop of many particle diagram. I could look at a cut that looked at that pair of channels. So the channel involving these two momenta, and then these three momenta. Well, then I'll end up with a situation where there's two massless momenta down here, and all three of these up here. So I'm just taking those into account in this diagram. That's all I mean. So yeah, it has to do with the contraction of the propagators that are not involved in the singularity, in the pinch.
This is a purely one loop statement.
At the moment, everything is one loop. Yeah. And now I'm going to go to, in a minute I'll go to two loops. Yes. If there aren't any further questions for now. No, Steinmann is an all loop statement. Yeah. 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 Everything I've said about Steinmann over here was an all loop statement. Like the what? So this is the concrete statement here. If I just allow this pair of Mandel-Steinmann variants to be anything that's partially overlapping and involves at least three massless particles for each of them, then this is always a true statement. Strictly speaking, that's not what Steinmann proved. Steinmann proved it in the case where there's masses running around. This is the empirical generalization, which is true in all known cases. Yeah. Okay, so let me now take a slight detour before telling you what the punchline is going to be at two loops. by defining what I refer to very quickly there as minimal cuts, which are in the title of the talk, so I have to get there. So as I highlighted in this massless box example, it's actually a bit unclear once you start finding non-trivial, interesting solutions to the Landau equations, what cuts you ought to associate with a given singularity. So here we had the s equals 0 singularity. You might think, oh, I should associate with a bubble, or you might think, now you should associate with the box because all 4 propagators are on shell. Or more generally, you can get very complicated singularities that involve many propagators that are involved in pinching the contour in some way that go far beyond what our kind of naive expectation is, even for these threshold type singularities. So that's where what I'll call minimal cuts come in. So this is an idea that we actually introduced over here to help understand or derive hierarchical constraints. But here, we can use minimal cuts again to tell us what set of cuts we actually ought to associate with a given momentum channel when looking for violations of the Steinmann relations. And let me just give you the intuitive definition of minimal cuts, which I can make more precise if you want. And that's more or less that we want to look for any possible cut that allows me to resolve the relevant kinematic degrees of freedom that are needed to define the location of the singularity in the space of external kinematics. So in these cases, it's just going to be something like a single Mandel-Steinmann invariant equals 0. So, but let me show you why. So at one loop, this is a bit overkill, but at higher loops, it's going to be relevant. So let me just highlight in a simple example when things start to become a little less trivial. So we might ask, for instance, what the 2-particle cut associated with S12 is in this diagram, if this is 1 and 2. So in this case, we'd have a pair of minimal cuts that are possible. We have this case and this case. And the point is that both of these cuts fully separate the kinematic invariant I'm interested in, which is S12. I'm interested in the singularity that happens when S12 equals 0. And so I just want to consider all possible cuts that, when I contract the non-cut edges, allow me to resolve that variable. So in this case, we'd end up with a pair of possible cuts, one of which looks like this. So that's kind of the intuitive one. And then the other cut actually ends up looking a little less intuitive. What we've done is we've separated particles 3 and 4 with the cut. But the point is that once we've left the physical sheet, we can have extremely complicated solutions to the Landau equations. We can't rule out something like this from contributing to the S12 equals 0 a new solution that gives rise to a singularity in S12, because you can have soft particles around all kinds of stuff. So this is the general way we think about algorithmically associating a set of cuts with a given singularity, in this case just singularities that appear when one of the Mandel-Steinmann invariants goes to 0. And it's minimal in the sense that if I were to have not cut any one of these lines in these 2 examples, either this pair of vertices or one of these pairs of vertices would have contracted into each other, and I would no longer have been able to resolve the sum of momenta coming in P1 plus P2. So for instance, if this propagator had not been cut, I would have ended up with something that looked like this, with 1, 2, and 3 coming into the same vertex. And clearly I cannot resolve just the sum of momenta P1 plus P2, because I can't distinguish it from the sum P1 plus P2 plus P3. So that's the idea behind main cuts, or minimal cuts. Essentially, they're going to tell us what cuts we should actually look at to look for the types of cuts we expect to give rise to Steinmann violation. And when I start talking about minimal cuts associated with pairs of channels, the same exact idea applies. It's just that I cut all the particles associated with the minimal cut for each channel. So I can go through an example of that if you like, but I'm running out of time, so hopefully that's sufficiently intuitive that when I do maybe a couple examples at the end of the talk, they'll make sense. Okay, so good, to get to two loops. So we're interested in making statements at two loops because no one's going to give us an award for explaining one loop singularities. So the first thing we can do is we can say, well, we know what singularities violate Steinmann in one loop. Let's just upgrade this to some solutions to the Landau equations at two loops. One of the first things I can do is I can always just replace a massless particle by a massless bubble, because when I solve the Landau equations, what they're going to do is they're going to end up setting both of these massless particles to be collinear, and so I can end up treating them as one effective massless particle. And so in that way, any solution that was valid of this one loop box, I can immediately upgrade to a solution that's valid when I have one of these bubbles instead of a propagator. So that immediately gives me 3 new cut topologies that I expect can give rise to Steinmann violation. These 3 guys. And then there's one more move I can make, which is there's something called the Y delta move, which is known in many, not all cases, but most cases to maintain or preserve the solutions to the Landau equations, or at least the first type solutions to the Landau equations. And I can apply the Y delta move to, for instance, this corner here, where I replace this 3-particle vertex, which looks like a Y, with something that looks like a delta. And I'm going to end up with something that looks like this. And so we can also use that rule to upgrade the solutions to the Landau equations we have here to solutions to this type of cut. And we can confirm that they have these solutions have the properties we expect of them. And so the upshot is going to be that all of these Landau diagrams or cut diagrams we expect can also lead to violations of the Steinmann relations if we see them in a 2-particle Feynman integral. Okay? So the question after that becomes, what about more general? What about other 2-loop cuts? And here's where I'm just going to state a conjecture. The conjecture is going to be that there are no further partially overlapping cuts or minimal cuts associated with these with a pair of partially overlapping momentum channels that I expect to give rise to Steinmann violation. So conjecture, a 2-loop Feynman integral can violate the Steinmann relations only if one of the above cuts appears. And when I say one of the above cuts, I should really include not just those 4 diagrams, but also this as a possible cut. Okay? So at the moment, this is a conjecture. It's an informed conjecture, given all the explorations we've done, but we can't prove it. But we can check it in many examples. So there's a lot of 2-loop integrals that have been computed that you can just go and check the answer in. And let me again highlight that I'm only talking about the first 2 discontinuities in a Feynman integral. I'm not saying anything about extended Steinmann. So when I go and check this prediction against all these 5- and 6-point integrals that are in the literature, I'm really only looking at the first two entries of the symbol or the first two discontinuities that appear in these integrals. Let me give you a couple of examples that illustrate how this works. So one of the examples we might look at would be this non-planar double pentagon. Okay. And I might ask, what would happen if I looked at this pair of two particle momentum channels, right? I have this pair of momenta coming in from the left versus this pair of momenta coming in from above. And hopefully you guys can see fairly easily that if I contract the two edges that have not been cut, this guy will turn into exactly, sorry, this third leg also is not cut. This guy will turn into exactly a cut diagram of the type we were talking about before, where now I've got a bubble over here, so it's the guy on the top right there. So we do predict with this conjecture that the Steinmann relations can be violated. And of course I say can because we're going to look at this integral in the literature where maybe, I don't remember the exact number, but there's some number of master integrals associated with this topology with different numerators. In general, what we see is, of course, any given one of those integrals may or may not violate Steinmann in this pair of channels, but at least one of them does, effectively. So the space of integrals does. And indeed, so we see that this prediction is, in that sense, confirmed, although of course that's a very loose sense of confirmed because we're saying can occur. We're not saying it has to occur. But a more interesting example might be the following one. So we can look at something like this. So I might look at the pair of channels corresponding to S12 and S14. So that's this pair of channels. And since this is a non-planar integral, indeed the final answer can and will depend on both of those two particle Mandel-Steinmann invariants. And a priori, I wouldn't have been able to tell you 2 months ago or 3 months ago whether or not I expected the Steinmann relations to be violated by this pair of two particle invariants. But if you were to go, I'm not going to draw them all on the board because I don't think it's all that illuminating. There's order 10 minimal cuts you can associate with this pair of two particle invariants, and none of them looks like one of these four diagrams or the one loop diagram we saw. So our prediction, and this is a real prediction here, it's not that it may not appear, it's that it will not appear. Our prediction is that Steinmann will not be violated by these this pair of two particle channels, and indeed we see this is true in the answer. So more generally, we can go and check all the integrals we can find in the literature. So we checked our predictions against all 5.1 mass, 5.2 mass, and 6-point massless integrals that have been computed. So overall, I think this was something like a little over 1,600 integrals. There's probably some duplicates in there when we look at the full spaces, but we're looking at all the subtopologies of every family of master integrals, so that's why there's so many. And I should highlight that our predictions get more refined as we look at these subtopologies because, for instance, if I contract this edge or something like this, I will start to lose cuts that I had before. And so actually we predict fewer Steinmann violating pairs in the subtopologies than we predicted in the top level topologies, and this is part of the check. This is all satisfied, and so we've got a lot of validation of this conjecture, and Our hope, of course, would be to be able to really prove this, but at the moment, that's where we're at, is that this is a conjecture that, as far as we can tell, is maintained by quantum field theory. So let me just highlight practically what this means, and so stated in a slightly different way. If I were to want to predict whether I expected my Feynman integral at 2 loops to violate the Steinmann relations, what I would do is I would go and just compute all the minimal cuts I associate with the given pair of partially overlapping momentum channels. I would then just compare to see if any of those cuts resembled one of these guys, or the one loop cut I highlighted earlier. And just to be clear, I should have really drawn in the cuts here, because it's not allowed to be the case that just these graphs appear. It has to be that the relevant cuts are really the momentum flowing through the left and through the top of the diagram, if you will. And with just this graphical rule, we can really predict whether we expect Steinmann can be violated in these 2-loop graphs. And let me conclude with that, but let me, as a last statement, just highlight there's a stronger and a weaker version of this conjecture. And at the moment, I'm only comfortable making the weaker version of the conjecture, which I've made here. And that's when I stated this is a 2-loop Feynman integral. In principle, we could also talk about a 4-loop Feynman integral, where if I looked at a pair of partially overlapping channels, all of the minimal cuts themselves were only 1 and 2 loops. One could hope that also one would be able to make a prediction in that case, but the singularities of Feynman integrals are subtle, and there are reasons or arguments one can construct where you might run into an issue there. So we're not yet sure on that case, but there is a chance of hopefully being able to make this conjecture or statement a bit stronger even. So that's the long-term hope. But let me leave you with that for now. Thanks for your attention. Okay.
But we didn't phrase it like that because we didn't know what the relations were.
Okay.
But we did see, in fact, that the analytic structure is very strange with overlapping discontinuities. I mean, we can discuss it.
Yeah. So that sounds very interesting.
And then you can tell me if you can use this.
Okay, that would be awesome. Yeah, we've seen maybe hints of this, but I wouldn't be able to say anything at the moment.
It's not trivial how the link and the infrared singularities work, because the violations are not in the infrared singular parts, but they're pieces.
Right, they're intersections with the infrared singularities. Yeah, it's very complicated.
That we could define in a very precise way that they're linked to the infrared singularity.
Okay, awesome. No, that sounds very relevant. Thanks. Thanks for the comment. Yeah, Jorgis. That's fine. Why do you say that? According to who? Steinmann? He wasn't talking about this, so it's according to us 5 years ago, right?
Well, no, already according to Cahill and stuff,
Okay.
back in the 60s and 70s,
Weren't they considering masses though?
they were clearly stating that Steinmann relations call for 3 particles at 100 something high. That's
Sure.
why I would, yes, we can look up the literature from back then. I would call them double discontinuities involving 2 particles.
All right.
Don't call them Steinmann particles.
Fair enough. Fair enough. You,
Steinmann relations do not talk about them.
I don't think the Steinmann relations talk about any of the massless integrals we've applied them to. So I don't feel strongly compelled to conform to the literature from 60 years ago. I guess that's my statement.
You say yourself that what we're discussing does not relate to massless versus massive anyway.
Yeah.
So it's true that Steinmann relations, we agree on this, we derive from massive like look at, you can just give justice to past work. That's all, as a problem.
Okay.
Yeah, so we could try move the discussion for later, right? Later, any more questions?
Yeah.
So you mentioned that when you look at the subtopologies, then you find less instances where Steinmann operation can happen.
Yeah.
I guess that never the point.
That's correct. It's never the case where you get more Steinmann violating cuts. Because if you think about the top level topology, you have some set of cuts you can generate with that. If you start contracting diagrams, you can't generate new cuts. Yeah. Right. So that's what's kind of fun is if we compare to these calculations done via differential equation methods where you have this hierarchy of topologies, well, you see that the top level topology does have Steinmann violations that the subtopologies that they're built out of don't.
Yes. In some sense, once you establish the mechanism, then there is only a point to study the topology. Once this is understood, then the new information always comes from the topology.
Yeah. Well,
Know that the subtopology is going to follow through.
oh, that's true. If you're only interested in one integral, you're saying.
In that class, by studying the topology, you know what they are. If you contract ones that are not part of the thing, or not part
Sure. Yeah, you could do the contractions at the level of the cuts, you mean. Yeah, that's true. All the information is contained in the top level topology. Yeah, definitely. Definitely. Thanks.
I can see it, so let's thank everyone for this one.
Thanks.